Welcome back. In the last video, we finished off coding the MLP block. Oh, excuse me. We got a little bit of a typo here. This should be MLP block. Beautiful. But where were we? So we've now done equation 1, equation 2, and equation 3 in reusable PyTorch code. So what's next? Well, it's time we put together equation 2 and 3 to create the transformer encoder. Creating the transformer encoder. The transformer encoder is a combination of alternating blocks of MSA and MLP. Now, if we jump into the keynote, we can get a little bit of a colorful overview. There's equation 3. And if we just map that to code, this is what we did in the last video. We've got our MLP layer, which is here. We create it by using alternating layers of linear and non-linear and put a dropout in between or after each of our linear layers. Then there's also a norm layer, which we created here using torch nn.layerNorm. And then we put it all together using a forward method. But there is still something missing from both of our MSA and MLP blocks, and that is the residual connection. Now, you might want to think about how we could implement a residual connection in the forward method here, in both the MLP and the MSA block, or we could implement it when we create the overall transformer encoder. So now let's map this. So if we have a transformer encoder, which is alternating layers of equation 2 and 3. So if we see here, this is from section 3.1 of the paper. The transformer encoder consists of alternating layers of multi-head self-attention, MSA, so this block here, equation 2, which we've already turned into a code block, and MLP blocks, which is of course equation 3, which is what we turned into a code block in the last video. Do we have residual connections here? I haven't highlighted it, but we have this line here, which says layer norm is applied before every block and residual connections after every block. So let's go back to the Colab, and we'll just write here. So this is equation 2, and this is equation 3. And we'll go here, and there are residual connections between each block. So we'll just make some definitions here. So if you want to know what an encoder is, you could look this up. What is an encoder in machine learning? You might be able to guess here. Encoder-decoder models allows for a process in which a machine learning model generates a sentence describing an image. So that's one use case of it. What is an encoder, decoder in deep learning? Encoder, decoder, what and why? Autoencoder. Machine translation, encoder, decoder model. Encoder and decoder. So we could go through all of those, or we can sort of infer what's happening here. So if we pass in our embedded patches and it goes into a transformer encoder, what is happening? Well, first and foremost, we've turned our sequence of image patches into a learnable representation or an embedding, and then it's going through this encoder layer multiple times to further learn that representation. So we could think of an encoder is turn a sequence into learnable representation. And then subsequently, what do you think a decoder could be? Well, it would be go from learned representation back to some sort of sequence. So if we go to Google Translate, one of the most common use cases, so we say machine learning is amazing, and we translate that into maybe Japanese. So Kikai gakushu wa sugui. That may be wrong, but what's happening here? Behind the scenes, if a machine learning algorithm is running this, well, the encoder will turn this into numbers, and then the decoder will deconstruct those numbers into another sequence. So essentially, we've got sequence to sequence. So sec to sec, or sequence to sequence, sec to sec, here we go, is usually a model used in family of machine learning approaches used for natural language processing, but this is where the idea of an encoder-decoder comes from. Recall that the original transformer paper was introduced for text problems. So attention is all you need. So that's where the name transformer encoder comes from. And what are we dealing with? Well, we're dealing with a sequence of image patches. So the transformer encoder is to turn that sequence into a more learnable representation. And then the decoder, well, we don't have a decoder in this architecture, would be to take the output of the encoder. You could probably actually call the MLP head our decoder, but it's not officially called a decoder here. But the decoder would be to translate it into another sequence rather than just a class name. But because we're focused on image classification, our output goal is a single class name rather than a sequence. So if we go back here, one more thing we're going to define, residual connections equals add a layers input to its subsequent output. This enables the creation of deeper networks, and it prevents weights from getting too small. So that's the idea of residual connections, encoder and decoder. And now if we do it in pseudocode, and of course you can research all of these different topics. Let's create it in Python, and we've got our transformer encoder. So what are we going to have as our input? Let's just call it X input, nice and simple, the output of our embedding patches or our sequence of embedded patches. And then we're going to, I'm not going to set it equal actually, we'll pass it through an MSA block, which is equation 2. Then we will create the MSA block output, and we will also add, this is the residual connection, plus X input. And then we'll go through the MLP block. So we're passing this here through the MLP block, and then we'll pass to the next section, the MLP block output, plus the MSA block output, plus X input to the next. So really this is just, I've done it like this because it's in pseudocode, but really this is going to be a single vector. So let's see what that looks like in Python or PyTorch code. So we create a class here, and I might call this the transformer, just nice and simple, nn.module, transformer encoder, nn.module. So actually, before we start to code it out, I think this is something you can handle. We might call this block, because we've been saying block a lot as well. So see if you can create the transformer encoder block using a combination of MLP block and multi-head self-attention block and residual connections. So what you'll be trying to replicate is, if you come into here, you'll want a forward method that passes an input through the MSA block, adds the input to it, and then same thing again, but with the MLP block. So give that a go, and then we'll create a transformer encoder together in the next video.